The reason that Radix is needed is that the industry currently faces three key challenges. The first is lack of scalability. And people talk about this all the time, right? And they have numbers on it. They go, oh, Visa scalability, 2,000 transactions per second. Or they say, the stock market scalability, 100,000 transactions per second. But ultimately, that's not the metric that we need to concentrate on. The metric we need to concentrate on is something a bit more abstract than that, and I'll go through that. The second problem is difficult to build on. Solidity in the EVM is a really interesting piece of technology, but it's fundamentally flawed because it's very difficult for a developer to come up, pick up, use it, and make sure that it's secure. And the last thing, and this is a bit abstract, and I'll go through this as well, is price volatility. Price volatility is great for traders, but it's actually not so good for businesses and for people looking at using it as a core part of their infrastructure rather than just as a speculative instrument. So, scalability, buildability, and low volatility are the three things that we need to address. First thing is scalability. Now, my point on scalability is that it doesn't matter if you can do 2,000, 10,000, a million, a billion transactions per second. What actually matters is looking at the abstract problem. You have 7 billion people and 24 billion devices. You want this infrastructure to be the same as the internet is, as TCP/IP is. So you need to have a technology that can scale to everyone using it simultaneously without there being a bottleneck to the technology in the first place. So it's not going, oh, we can do a billion transactions per second. It's going, will this work for everyone in the world using it simultaneously over an extended period of time? Now, the reason that's difficult isn't just how much throughput you have, it's also because you have to do storage. Because unlike the internet, you have stateful information. You have to remember that I sent you some tokens so that the network can say, okay, it's okay that he sent those tokens to someone else. So you've got this big data problem. So what we did is we said, well, you're going to have to shard it, because if you're storing that much information for everyone, then it's going to be a massive database and it's going to have to store a lot of information. So let's just make it sharded enough that it can do that automatically from day one. So it's 18.4 quintillion shards. And so how do you know that's enough data? How do you know that you can store enough data on that and you're never going to get to the point where you have to change the shard space? Look at Google, it stores about 10 exabytes of data. That's all of YouTube, all of cloud services, all of their Gmail suite, all of their search engine. That's 10 exabytes of data. You divide that by 10.4 quintillion, and you come up with half a byte per shard, 4 bits per shard. Which means that we could literally dump everything that Google is storing right now into our data structure, and we would only need 4 bits per shard to be able to store that data structure and cut it up efficiently. The second thing that happens then is if you've gone, oh, we've got 18.4 quintillion shards, we're never going to change it, is that you can make things deterministic. You say your wallet address determines where you live in this space. So if you have a shard space and your wallet address is some hexadecimal number, and then you modulate that down to 2 to the power 64, goes you live on shard 526. And because it's deterministic, it will never change. You'll always live on shard 256, which means that you can always address that space. It's very easy for you to be able to go to the part of the data structure and go, I want my information back. Unlike blockchain, which is you just have to go through every single block and go, is some of my data here? No. Is some of my data here? No. Or a DAG, which is basically a soup of unstructured information, which becomes very difficult at high scalability. What you get here is you also get some really interesting features. The first is you group together related transactions. If you're deterministic that you live on shard 256, that means that all of your transactions start from there. So you can only double spend on that shard. You can't double spend across 256, sorry, 18.4 quintillion shards. And then you ungroup unrelated transactions. If I send some money to my mother and Sophie sends some money to her mother, those two transactions are not going to be on the same shard, but they're not related, it doesn't matter. So you get this massive asynchronicity. And actually the asynchronicity of the network is 18.4 quintillion, which means that you have a throughput capability of 18.4 quintillion times the throughput of one shard, which is more than enough than we would ever need in the feasible heat death of the universe. So, and the last point that happens here is because you're grouping together related transactions and you only need consensus on related transactions, you can actually have a very efficient node balancing, where you have nodes that could be Raspberry Pis servicing a small part of the shard architecture, or you can have nodes that are massive servers that can serve the whole of the architecture, but it still allows you to be able to have this massive throughput. So the second point is buildability. Buildability on Ethereum is difficult because, not because the tools are difficult to pick up, like Solidity, it's sort of a JavaScript-esque language with some weird quirks, but actually making sure that it's secure once it's built is incredibly difficult and very expensive. You have to go and get smart contracts, audits and things like that. So what we did is we decided that actually building smart contracts is probably not the best thing for most developers wanting to build against a DLT. What they actually need is APIs that just behave according to how they used to program it, and that they can call against the ledger exactly what it is they need. If I want a token, I call against the API and then return a new token. If I want to do a multi-sig contract, then I just call against the APIs and I return a multi-sig. You don't actually need to have all of that smart contract complexity to be able to deliver most of what people wanted to build on a DLT. The last thing is it's fully asynchronous, which means that you get this really nice paradigm that's used in most programmers if you're using the RX Java or something like that against a standard server-based architecture. But this time you're doing it against a DLT, but you don't really see any of that. It's all dealt with behind client libraries, and all you have is these nice responsive APIs that you can program against. The last point of this is low volatility. Now, a lot of people like the volatility of these underlying cryptos of Ethereum and Bitcoin because it's been great for speculation. The problem is you've got two sides of this paradigm that are really important. The first is the node runners, the people who are actually running the network. What you don't want is the incentives of the network to dry up such that they just disappear. Because if they disappear, then there's no network, so there's nothing that you can actually use in the first place. On the other side, you've got the people who are looking to pay for the use of the network. If I'm a company or a developer, and I'm like, I want to base a key part of my infrastructure on this technology. If the price of the underlying moves about too much, you end up getting this problem where you can't actually predict what your costs are going to be. And then you can't do a very simple calculation of what your gross profit is. The revenue minus your input costs, if you don't know what your input costs are going to be for the year if you're using this infrastructure, if you don't know that you may actually be underwater the next time you make a sale on top of this platform because you're basing key parts of your infrastructure on it, you've got a problem. And equally, if you're thinking about investing in computer equipment to do mining or to do node running, and you can't actually predict what the revenue is going to be and whether or not you're going to be covering their electricity bills, you've then also got a problem. So underpinning the Radix system is also a system of economics, which makes sure that the maximum cost of use and the minimum revenue for suppliers is bounded to help make sure that there's predictability in the use of the network and predictability of the income that you get out of actually providing resources to the network. So those are the three things: scalability, buildability, and volatility. We will be live in Q4 of this year, but in the meantime we have now Net Up, which is doing 2,000 transactions per second, which you're very welcome to come and try and break, which we like when people try and do that. And also the APIs are already available that you can start building against our JavaScript libraries, our Kotlin libraries, and our Java libraries. You can also find more information on our website. Our docs are available, which goes through the technology and how all of this works and the theory behind it, as well as the tools that you need for that. There's the forum, where you can join the conversation, ask technical questions, and there's also Telegram, where you can get involved in the community. Thank you very much.